And please welcome Julian to the stage.
Good morning, everyone. I'm so glad you're here. So to start the morning off, I want to invite you to do something with me. I want you to imagine a typical engineer at their desk analyzing data. Now, you don't have to specify, or I don't need to specify where, just whatever comes to mind for you. Now, while you're doing that, I want to see what comes to mind for AI. So I'm going to ask the same question, a typical engineer or an engineer at a desk analyzing data. And this is what AI imagined. Now, I don't know how much this lines up with your thought. This person looks kind of stressed. They're obviously not a JMP user. But obviously, you know, they're dealing with something. They're stressed at their desk analyzing data. Now, of course, what AI imagines is not the real world, but AI generates images like this based on training data, which is in some ways a reflection of the world. It reflects some of the beliefs of society. It reflects some of the biases of society, and you could probably spot a few. But to some degree, it reflects some underlying truths that exist out there in the world. And so if you'll allow me to, or just indulge me, I want to speculate on what's stressing him out, because these are things that we hear from engineers all the time. Now, I'm going to guess that he might be thinking, this is not my job. He's tasked with doing data analysis, but he probably wasn't hired to. He has substantive work to do. He's actually connected to the processes that he's measuring. He does real engineering work, but he has to analyze data because now it's part of his job, even though he wasn't trained on it. He's probably also thinking that this requires others. There are dependencies on other people in the organization, people that don't report to him probably, dependencies that make his job harder, and especially because those people don't care about his deadlines the way that he does. He may be thinking that this is too complex. He doesn't have the right tools for it. Again, he doesn't have JMP. So he might be thinking that this is too big, too hard. He's not trained on this. This not being part of his job probably wasn't also part of his education either. And finally, and in contrast to this, he might be thinking this is too monotonous, every day doing the same thing. So it might not be too complex, but it does wear him down because it's just something that becomes boring almost. So, I'm so sorry, I now have gotten lost in my slides. So this may be a caricature of what an engineer does, but I do think it has some truth and reflects the real world. Because as I said, these are things that users have told us as we go out to sites and talk with engineers. Those are real problems that engineers actually face. And so it's part of the reason why when we think about the design of JMP and we build in JMP, we make the choices that we do. And as Jeff said, you know, JMP has grown enormously throughout our 35 years. And more recently, we've actually focused on certain places in the software that historically have had associations with data science. So things like data access, accessing cloud storage, first-party connectivity to open source languages, predictive modeling, machine learning, and certainly automation and scripting, right? We focused on these things because we hear from engineers that these are parts of their job that they actually need tools to help solve. But of course, these aren't the only places we invest. We also think about the entire product and augmenting features to make it easier and less monotonous and more possible for engineers to do their work. And to do so in an approachable way. Because of course, it's not only that JMP has features and functionality, it's that JMP helps you do these things and feel good analyzing your data, to actually have fun with it, if you will believe me on that one. So our speakers this morning are going to show us the ways that JMP makes possible data analysis, how it makes palatable complex analysis, and allows us to really get the most out of our data and find the insights that we need to do our jobs, which, again, oftentimes are not specifically data analysis. So to start us off, I want to invite our first speaker to the stage, Valerie Nedball, to tell us a bit more. Valerie?
Good morning, everyone. I'm very happy to be here, and I hope you too. So, thank you, Jules. I'm Valerie Nedball. I'm working at JMP already a long time, and I recently joined the product management team, so I am now product manager for health and life sciences. Before joining JMP, I was working as a molecular biologist, so believe it or not. And I was always fascinated by understanding the disease risk factors and commonly associated by genetic factors. So genetic data can be quite challenging. Genetic data can be quite challenging as genetic data is vast and complex. And genetic or marker variation, or sometimes we call mutations, are often linked to diseases. And finding marker variations is like to find the needle in the haystack. But not only marker variation, but also environmental factors or lifestyle also play a role in disease outcomes. So in the short presentation, I just wanted to show how easy and fast it is to deal with such challenging data using JMP. And I decided actually to use something that I'm related with disease outcomes. So I decided to choose diabetes type 1 worldwide incidence and risk factors. So first of all, I had to look to find a good data set to represent incidence worldwide. So I looked around in the internet and I found actually a good database, Institute for Health Metrics and Evaluation. And the data looks like the following. It's a quite huge data set, it's about 20,000 rows, and each of the rows is represented by location, by the age group, by the year, so the year spans from 1919 until 2021, what's the gender, and of course the incidence. So my first question was actually, what drives the incidence? So which of those factors drives the incidence? Well, a very easy and fast method is using the fit model. So the fit model allows you to do lots of different models, and I just wanted to show here how easy and fast it is to do. So I use actually all the 4 different factors as an effect, and as I did not know if there are any interactions between those factors, I decided to use a response surface. So you can see we have here main effects, but also all sorts of interactions. And of course, I use the incidence as my response. I click run, and very fast I could already have some answers to my questions. I can see that all my factors are very significant, and I had a very good model. So I was really surprised, I said, wow. And of course, the next question is, what drives actually the incidence? So the next step is to use the prediction profiler. You can find it here. So while I'm opening that, you will see here the prediction profiler on the bottom of my report. I make it a little bit bigger so that everybody can see it. So what you can see here is actually the prediction of the incidence by the effects that I have put in the model. So we have the location, the age groups, the year, and the sex. And you can see that the location has a huge impact. So whenever I'm changing here my scroller, you can see the impact on the incidence. And my first question was, well, okay, what is actually the region where I have the most incidence? And I can see the Commonwealth high income. And you can see whenever I'm changing this cursor, you can see a huge interactions with the age group. And I was also surprised, but in the literature, I was not surprised afterwards, but I was really surprised that the young people has the highest incidence. So we are here in Berlin. What is the incidence here in Western Europe? So Western Europe, as it is sorted here alphabetically, is quite at the quite end. And again, I was quite surprised that here in Western Europe, we have also a very high incidence of this disease. And you can also see this trend in the age group, and the trend is actually increasing from year to year. So by the fit model, I could already answer lots of questions. So the next step is to find actually what are the risk factors. But before going to that, I just wanted to explain you a little bit what the disease is all about. So diabetes type 1, about 9 million people worldwide are living with this disease. And the cause is an autoimmune condition where the immune system attacks the insulin-producing beta cells in the pancreas. So you can see that the beta cells get destroyed, and the consequence is the body produces little or no insulin. The causes are quite unknown, but in the literature, I could find already some risk factors associated to the disease. And there's a particular region on the chromosome 6 of the human, where we had, or the literature has already found some association with the disease. And I was lucky enough to have a data set where I have marker that spans on this region. So here's the data. So this is a typical data from genotypes. So you can see 1,1, 2,2, 2,1. So it's what allele are actually on the DNA. And you can see that each row represents one particular patient. And this particular patient was diagnosed by diabetes or not. And all those patients were genotyped at about 2,200 different markers. So now my next question was, I have now this region, which kind of genotypes or which kind of allele are really associated to my disease? So a very fast way to do that is to using the response screening. The response screening is under the screening and response screening. And this is a very powerful platform in order to screen all sorts of whatever effects, in my case, are markers. And I want now to screen all those markers with my diabetes status. Simply click OK, and you can see that I have already the answer to my questions. Here are all my different genotypes that are very significant to my disease. So next, I wanted actually to position my markers on my chromosome. So you remember, I had this region of 2,200 markers. I wanted to position now on the chromosome. So the only thing that I had to do is to use now the data table. So I have now the data extracted from our report, and now I have to join this data to another data that will tell me at which position this particular marker is located. So let me clean that a little bit. So I have here another data set. So it's an annotation data where I have the position of those markers. So I make a join with my data from the response screening. I join with the common variable and click OK. And now I have here my data. I have the position, and I have also all my significant tests like FDR or p-values. So I use now the graph builder in order now to position now my different markers, make it bigger, position on my X, and my FDR log worth as my Y. And I was really surprised again. So I had here a hot spot of markers that were really significant. And okay, this is not the end of the story. It's now, well, can I validate really where those markers are? So by mousing over, I could see a label. And on this label, you can see X with an identifier. So I only type this identifier on the internet and look where this marker is positioned. And no surprise. It was located in the HLA DQ, and the HLA DQ, if you could see here on my little map, was exactly located here in this particular gene. So by a few analyses, I could already identify risk factors, incidence worldwide very quickly. So I wished I could do some more analysis, but I don't have time for that. But it would be great if I could do these risk factors with subgroups like age groups, like regions, like years or gender. But I had no time to do that, and maybe we will see that further on in the presentation. So that's it for me. I'll leave now the stage to Julian.
Thanks so much, Val. Yeah, JMP really has a way of making complicated data analysis easy and friendly. But that's not the only reason JMP is kind of magical. Because it's not only what JMP enables, but also what it encourages. And JMP has a way of encouraging adventurous, ambitious data analysis. And in fact, we've always thought of JMP this way. If you go back to one of our earliest sample data sets, Big Class, you'll notice that there's a notes property in all the columns that is even trying to encourage you to explore data adventurously. And so this is a thing that JMP has always been all about. And so to tell us more about that, I'd like to invite our founder and chairman and the first developer of JMP, John Saul. John?
I'm going to talk about screening. Screening is the act of sifting through a large amount of data, looking for the few big, unusual, interesting, and important effects among the many. Looking for needles in a haystack, diamonds in the rough, four-leaf clovers. We look for anomalies, excursions, patterns, outliers, missing data patterns, hidden relationships. And in JMP, there are many screening platforms. In the screening menu, we have Explore Outliers for looking at rogue data points. We have Explore Missing Values that includes imputations so you can fill the holes in your data. We have Explore Patterns for looking for suspicious data that might be fraudulent. And response screening, as Valerie just showed, when you have many Ys or many Xs and sometimes many groups. And then there's predictor screening, when you have lots of X's and you want to find out which ones best predict the Ys. In the quality and process menu, there is process screening to look at data, time series data in the statistical process monitoring theme. And in fit model, we have the fit response screening for fitting a model to many responses or many groups and so on. So, screening platforms in JMP, and we're going to focus for the next few minutes on response screening and fit response screening. So let's take a look. So here's a data set with almost 1 billion cells in it, 948 million cells, 17,000 rows, and a set of genes, 54,592 genes. So let's look at response screening among groups. We're going to look at all those genes across both age and sex individually, grouped by the Hardy measure. And so let's take a 10-second wait here for it to do all those things. But we'll count by 10, so it's done already. Okay, and here you see the summary of all those tests. There's 540,475 of them. And you see the p-values marked in red. And you see the p-values plotted against the rank fraction of the p-values, so they're all sorted. And you know what the characteristic, if you have inactive effects that are essentially zero, what their p-value distribution is? Well, it's the uniform distribution at 0, 1, which would be represented by a 45-degree line in the distribution plot. And here you see that a lot of those p-values have the characteristic of a 45-degree line. But by random chance alone, that uniform distribution is going to have a bunch of p-values that look significant by random chance alone. That's what the p-value distribution means. And what we need to do, because we're sorting and selecting, there's all this bias in the p-value selection because we're doing that, and we need to correct for that. And there's something called a false discovery rate correction, and the one we're using is called the Benjamini-Hochberg method. And that corrects those p-values for all that sorting and selection. So if most of your p-values are insignificant, there's a lot of correction. If most of them are significant, there's only a little one. And you see here where the red line goes to that ramp there that goes from one side at the 0.05 level to the other side, the 0.05 over the number of tests, is where the adjusted p-values go below the 0.05 line. And so this gives you an idea of how many of your tests, after you adjust for that selection bias, are really significant. Now, we also have instead of using p-values are incredibly small for highly significant events. And you can't plot tiny values, so we'll take minus the log of those p-values, and then we'll get big numbers for the highly significant ones, and we call that log worth. So the FDR log worth for all these effects, and we can pick out the biggest one, which we see sort of at the top of the result table, is this one gene on the sex variable for the subgroup Fent. In fact, we can select the ones that are all significant. We see that pretty much all related to the sex variable rather than the age variable. So the variation is more related to sex than age. And then we can actually look at all the age relationships, and they're all pretty insignificant, whereas the sex have a lot of significant values. And we can look through the various groups that we've had to see which ones, and the ventilator ones are the most significant, and so on. So very quickly, we can pick out what are the strong effects among 500,000 tests. Okay? So let's take a look at another case, but this time using fit response screening on a slightly smaller data set. This is the breast cancer data. And we have, we're going to do the interaction, the cancer status, progesterone or estrogen response and HER2 response and pro status, the cancer states related to all these gene expressions. And then we're going to interact that with age. And so let's fit that. And that makes a lot of tests, but it's pretty instant because there's 75,000 tests, and most of them are insignificant. And in fact, we start looking at the effect size, and all the age variables are pretty non-significant. They're at the bottom of the log worth. And the ones that are significant are the cancer status, and especially the ER status of that. And if you look, you can look at what the biggest ones are, both in terms of effect size and significance. If it has a lot more data, it tends to be more significant, but if there's a bigger effect, it can be significant, but less significant, but still a big effect, and so on with fewer data. Okay, so we're able to screen all this data and find out which markers tend to be associated with breast cancer. So now, a lot of those, we calculate least squares means for all these effects. And those are means adjusted for all the covariates and so on, the rest of the model, to give a fair comparison of which levels are big and which levels are small on the response. So it's one thing to have a test about an effect, but it may be more valuable to exactly find out which effects inside that effect are large or significant. So some of the insides of an effect may not be important, but others, so it's the details inside a significant effect. So suppose you have an interaction of age and sex, where sex has 2 levels and age has 6 levels. This is the big class example. And you calculate all their least squares means, and you want to look at all the least squares means comparisons. Well, we have 12 different least squares means. If you choose all the comparisons, there's 12 choose 2 or 66 comparisons. But are all those interesting? We have examples like comparing the male 12-year-olds and the female. So that's within the 12-year-olds, does sex make a difference? Then we can compare the 12-year-old male with the 17-year-old male. So that means does age different within the males? So all those are meaningful. But what if we compare the 12-year-old males with the 17-year-old females? Well, 2 things are different, and so we don't know whether it's due to sex or age, and so it's not a meaningful comparison. So let's define, here's an example of all 66 comparisons. But what do we really want? And let's define sliced least squares means as when only one of the factors is different across the comparison. So it turns out there's a lot fewer sliced least squares means comparisons than there are total comparisons. So across age with 6 levels, there are 6 choose 2 or 15 age comparisons. So there's 15 within the males and 15 within the females, so that's 30 comparisons. And across sex, there's just 1 comparison, and we have 6 different ages that we have a sex comparison, so that's 6. So 30 plus 6 is 36 sliced comparisons, so that's a lot fewer than the 66 comparisons. So with slice comparisons, it becomes practical to compute all the slice comparisons. All of them are potentially relevant comparisons, interesting comparisons. There's no comparing apples and oranges that are different in more than 1 factor. And so let's look at sliced comparisons. So let's open big class, which has the age and sex in it. If you do all multiple comparisons, it's comparing all those apples and oranges, and there's 66 of them, but that's not the interesting ones. So let's use sliced least squares means in fit response screening, and this is in JMP 19 coming up next fall. And here we have all those differences, and so there's the age differences as a main effect, the sex differences as a main effect, and then the sex differences within ages 12 through 17, and then the age differences within the females and then the males, and here are all of them, their log worth against the least squares means difference, and you can look at some of the big ones, and age differences are pretty big. As a main effect, their sex just 1 point, not much difference. Sex within age is not so interesting, but age within sex is pretty interesting. So there's a lot of sex differences within each age group, okay? So sliced least squares means. So let's look at a bigger example, because we're all talking about analysis at large scale. So here's the fruit fly data, Drosophila, and we have lots of genes here, and we're going to look at differences among those genes, and we have a number of effects: the line, sex, age, and channel, and all their interactions. And so there's lots of these differences, and we're going to get all the sliced least squares means differences and see which ones are important. And so it looks like the biggest one is gene 131 in week 1, the male to female difference. And here's others, and they tend to be all male and female. And so if we select all those that are very significant, they tend to be on sex as a main effect, sex within line, sex within age, sex within the interaction of line and age. And we can also, if we look at a few of these tend to be all in the 131 group. And so if we look at 131 and look at all their effects, 131 gene expression tends to be pretty significant across some of those tests. So sliced least squares means. Let's look at the breast cancer data again, this time with the interactions with, and here we see the least squares means, and the biggest one is that gene at age 40, the PN group, and that's, if we select that, that's associated with the HER2 status within age group. That's the most significant. And then we can look at the others. Let's look at a bunch of them. And it tends to be the ER status within age group and the HER2 status within age group. But if we just looked at those individually, ER status and HER2 protein status, they're not very significant. So here's the case where they're significant within an age group, but not significant in general. And so we've dug in and found those differences that would have been subdued if we aggregate over too many things. Within age group, they are very significant. And so we're really making discoveries here by using the sliced least squares means. Okay, let's look at another aspect, instead of sliced least squares means, we're going to look at subgroups. So subgroups, have you ever done an analysis with bigroups to get a breakdown and then wanted to see the analysis with a different bivariable, and then without any bivariables, and then with two different bivariables? Let's say you have three variables and you want to look at all the breakdowns. If you have age, gender, and marital status, there are actually 7 different combinations to look up to 2 variables. There's all the data without any bigroups, aggregating it all. There's a breakdown with one bivariable by age, by gender, by marital status, and each one of these will have multiple groups, and then breakdown by 2 bivariables. And what if you wanted all the analysis to be shown together? Well, with subgroup features coming in JMP 19, that you can do. And supposing you have a lot of terms to check, you can do some of these subgroups by adding it to a linear model, but that has limits. You can't do hundreds of thousands of them, and with their high order interactions in a linear model, it's just too big. But you can analyze them as subgroups. It can be used with millions of terms. Switch variables are another technique available for many terms that you can do right now in JMP 18. So have you ever wondered if you might have aggregated out an effect that could have been important in a subgroup of your data? Suppose you have an expensive clinical trial to test a new drug and it failed, but if it didn't fail for everyone, if you could just identify the patients for whom it worked, then you could rescue the drug for those individuals. And so subgroups can be very economically important in cases like that. And so let's do a simple subgroup for age and sex, which gives you a flavor of 2-level subgrouping. So you have the analysis with all the data, with just the large, with the subgroup by size, subgroup by type, subgroup by marital status, subgroup by the combination of size and type, the combination of marital status and size, the combination of marital status and type, and so on. So there can be a lot of subgroups, especially if you do two-way interaction. So let's do an example using fit subgroups in fit response screening. And this is the maize or corn data. And I'm going to look at gene expressions again. This is traits 1 and traits 2 for each subgroup. And it turns out this is doing 308,000 tests. And here you have all the effect sizes and significance. And so within trait 1, this subgroup GG within that gene is actually the highest. And you can select out which ones are important by the subgroup. Okay? So you can do subgroups at vast scale. Okay? So subgroups are pretty interesting. Now let's look at another kind of screening. And this is process screening for time series production data. Process screening monitors many processes to determine if they are in control in a control chart sense, if they're stable, not shifting or drifting, and if they're capable, that is within the spec limits. And it can sort the processes by various measures, chart them, and provide various summary graphs. Now, previously, process screening was only for normal processes that monitored whether a process was near its target. But soon it will handle processes where you'd like to avoid large values, such as count processes, such as environmental contamination counts, where you don't want high counts. Non-negative processes, such as contamination rates. Proportion processes, such as defective rates in batches. And with these kinds of processes, you have, instead of control limits and spec limits, you have action limits and alarm limits. Action limits, typically, unless you have pre-specified action limits, it's it's a certain quantile of the distribution, the 0.9985 quantile, like a 3 sigma, and an alarm limit that's more of a warning rather than a call for action. It's like a 2 sigma limit, 0.975. And so fitting these distributions and finding the best distribution for the data. And so let's look at that in action. And here's some simulated environmental monitoring data. And let's look at process screening, where we have 3 grouping variables: the count variable, which is the contamination counts and across time. And we'll do process screening for the count type of chart. And here you see the ones at the top are the ones that have exceeded the action limits. And in fact, if we select those, each time we select them, the chart for that appears at the top. Let's select the first 4 that have action limits, and we see them represented there. And it also clues in on alert increasing, and so it's above the alert level, but not quite at the action level, but it's increasing. And so that's a warning sign, an early warning sign that maybe you're going to have an action later. And so there's something new called an alarm graph that shows where all those happen, those alerts happen on the time scale. And so I can pick that, or I can just hover over a point and see the process for that, or I can select them and see them as selected. And here's some action alerts that happen pretty much at the same time. And so if I select those 3, they pretty much happen at the same time. And look, this is in room 224 and this is in room 225. So maybe there's cross-contaminations between those 2 rooms, and then it may be extending to room 282 in a few hours later. And so this is a quick way of looking at that kind of data as process data. And you can supply your own limits table. And not only that, but you can publish this in JMP Live. And so if I publish that data, it looks like this in JMP Live, and here's our process summary. And even as you look at each one, it'll, as you select each one, you can select a number of them and see the details off on the other side, and you can look at the alarm graph as well. And so being able to publish this with JMP Live is a new feature, okay? So we've covered a lot. Modern data analysis often involves analysis at scale, thousands or millions of fits, comparisons, processes, and it can be done easily on the desktop or laptop with JMP. There are many directions for multiples, including many responses, many switches, many slices, many subgroups, many processes. In cases where you do statistical tests, applying a false discovery rate correction is important. In any case involving many tests, these adjustments can only be done in the context of a mechanism designed to do multiples, so it has to be aware of all the tests. And multiples demand summary plots and reports that are designed to focus on the relationships of processes that need attention. So there you have analysis at scale. Back to Jules.
Thanks, John. I'm always so impressed at how fast JMP can be for these immense-sized analyses. I just have to tell one story. A couple weeks ago, we were doing the rehearsals, and John got frustrated that some of these platforms were taking 15 seconds to run. So instead of change his presentation, he went back to his office and basically optimized the code and got into the C++ and made it faster so that it could only take a second, and so that he can demo some of these things without making you wait for 15 seconds, because that would be too long for 500,000 analyses, right? So anyway, just a credit to John's brilliance in programming. But as John showed, JMP is really great for these huge questions. And it's also incredible how the interactivity of the interface obviously encourages the exploration of data, and it lets you find things you otherwise wouldn't find. Now, it's not always the case, though, that the person who's doing the data analysis has all the expertise or skills to do the actual analysis and understand the results. And so it's not only about what JMP can encourage, but sometimes what steps and dependencies JMP can help eliminate from a workflow. And to tell us more about this, I'd like to invite Sarah Gilliard to the stage to give us an example of just that.
Hello, my name is Sarah Gilliard. I'm on the product management team here at JMP. Prior to joining JMP, I spent 16 years in the semiconductor industry. A semiconductor fab can be a very chaotic place. Fab engineers spend a lot of their day running around with their hair on fire, jumping from one crisis to the next. So what I'd like to show you today is how JMP and the Workflow Builder, specifically a feature I like to call Choose Your Own Adventure, can make the life of a fab engineer just a little bit easier. So to motivate this discussion, I'm going to use an example from a very common semiconductor process called shallow trench isolation. This process occurs sort of early on in the manufacturing flow of a wafer. This process etches trenches into the silicon substrate. Sometimes the plasma etching process might need to go through other films like oxide or nitride films before it actually gets into the silicon substrate. But after the trenches are formed, they will subsequently be filled with an insulative material that's intended to electrically isolate the different circuit components like transistors and such. So the response variable that we are going to use in this example is the depth of this trench. So the depth of the trench that gets etched into the silicon is our response variable of interest. And in this example, this process metric has been exhibiting excess variation, and we need to quickly source where that's coming from. So let's go ahead and go to the workflow. So this is a relatively simple workflow, but since engineers have to use a lot of discretionary judgment in their day-to-day job, a workflow should be able to reflect that. And this workflow could easily be shared across an organization and used on different types of processes with different variables with fairly minimal alterations made to it. So I'm gonna go ahead and run the workflow. So the first thing the workflow is gonna ask is, what data table do you wanna open? So I'm gonna go ahead and open our data table. And the first piece of analyses that we do is a variability chart and a variance components analysis. And the message that popped up asks me to review the variability chart and then click continue when I'm ready to proceed. So this is the first choose your own adventure piece of the workflow. The purpose of this piece of the analysis is to break down lot to lot, wafer to wafer, and within wafer variation. In a semiconductor manufacturing process, there's a lot of batch processing that gets done, so different process steps process in different batch sizes. So for example, a plasma etching machine might run one wafer at a time, whereas something like a diffusion furnace will run potentially 5 lots or up to 125 wafers at a time. So this means that there's a lot of very complex variation structures that get created in the data. And so to break down where that different variation comes from a batch standpoint can be very helpful to a fab engineer to help them pinpoint what tool set might be driving a variation issue or what process might be driving a variation issue. So what we see here is that the lot to lot comprises the bulk of the variation in this depth of our trench data. So I'm going to go ahead and click continue now that I've ascertained that information. And my workflow is going to ask me, well, how do you want to aggregate the data? Do you want to aggregate it to the lot level so that every row represents one lot? Do you want to aggregate it to the wafer level? Or perhaps you want to do within wafer, or maybe you want to do all. In this case, since lot to lot variation was the bulk of my variation, I'm going to aggregate this data to the lot level to perform my exploratory data mining, knowing that that's the source of most of the variation. So I want to focus in on what could be driving that particular bucket of variation. So I'm going to click OK. And some stuff just happened. So let's take a step back and see what we've done. So the first thing that our workflow did was it did the hard manual labor of aggregating this data up to the lot level. So now each row of the data table represents one lot, aggregated using the median. So Now, whatever additional analyses I might want to perform that's not part of the workflow, I easily have that data table available to me, and I didn't have to perform the steps necessary to do that. So this workflow does just a handful of analyses. First, it provides a control chart of the response variable. So in this case, a control chart of our trench depth, so that we can confirm that yes, our boss is not happy. The next thing that our workflow did is it performed the bootstrap forest analysis. So this is the bulk workhorse of the workflow, if you will, to try and pinpoint the culprit behind where this excess variation is coming from. A bootstrap forest is a very versatile, robust data mining technique. It tends to handle outliers and multicollinearity very well. So in a case like this, if you kind of need to just throw something at it fairly blind, a bootstrap forest is not a bad choice. And we can see that of all the process variables, there were about 30-ish process variables put into this analysis. We can see that there's a roughness variable, and that is associated with the roughness of a surface film. And there's also nitride film thickness and oxide film thickness that come up on top. So put that together along with our engineering knowledge, and it seems like we might have an incoming film thickness, or potentially just an incoming film issue here that might be driving our problem. So with that information in mind, the next thing the workflow has done is give us some ability in Graph Builder to look at our process trends. So now that we kind of think that we might have an incoming film issue, we can start to explore the process trends and just make sure that things behave physically the way that we would expect them to. And so we have a column switcher here, and we can run through all of our different process trends. And last, but certainly not least, the workflow publishes all of this output out to Jump Live so that you can share this with your colleagues and show them all the wonderful work you did in about 10 seconds. So thank you for listening, and we'll go back to Jules.
Thanks so much, Sarah. Yeah, building an adaptable workflow like that is just a wonderful way to use JUMP to eliminate dependencies on expertise in an organization. As Sarah said, that can be just shared with others, and they can too do that kind of complicated analysis that they may not have the training on. So that's a powerful tool, but the power of JUMP, or the magic of JUMP, is not always what steps it can eliminate. It's also what it can do to help you avoid work entirely, which of course is the best of all cases. And so I want to invite our next speaker on stage, Kristen Slappy, to tell us a bit about doing just that.
Hi everyone, my name is Kristen Slappy, and I am the manager of the JUMP Marketplace. So today I am here to tell you how the JUMP Marketplace can help you streamline, enhance, and customize your JUMP process. So like Jules said, you can just remove steps altogether. So how does it do that? It can help you bring your data from various data sources into JUMP. It provides out-of-the-box data visualizations and analysis to really help you streamline your workflow and process. So how do we get from the JUMP Marketplace you see here into JUMP? So we can just browse our extensions, and we have a couple different categories. So for the one I mentioned, bringing your data into JUMP. So a lot of times your data can exist in various different forms and in different places. So we are really working for JUMP 19 to build out our data connector library. So if your data exists in Amazon S3, which is the one I'm going to show, you can just bring your data into JUMP with no hassle. You can create those data connectors, send them to colleagues, just make it very easy for your workflow. And for those out-of-the-box data visualization and analysis, we have over 58, it's 58 right now, close to 60 extensions that do various things. So analysis and data visualization, we can see that we have about 27 that come up. One of my favorites, and the one I'm going to demo today, is this Capability Explorer that was created by Scott Allen, and it creates a 6-graph summary for process capability that you didn't have to create yourself. It's already been created by one of our JUMP staff members, and you can just download it and get it working within JUMP. So you just click download, you sign in with your My JUMP ID. So if you have JUMP 18 already, you already have a My JUMP ID. If you don't, you can easily sign up for one. You sign the user agreement, everyone's favorite part of downloading an app, and click submit. And you can see it downloads right away. I can just open this file, click OK. And it shows up within JUMP. So I can go to my add-ins, and I see it right here. So for this demo, I went ahead and set up my data connector. So I have one called S3 Europe Demo. On my left, I can see all of these buckets that I have within my AWS subscription. So this is pulling right now from the cloud, from a bucket, which is a fun way for Amazon, a place to put data. And I have these data tables within that bucket that I'm just going to pull right now. So it pulled it from the cloud for me. I've got my data table here, and I can now use this add-in for this process capability analysis. So I want to examine the variable weight, click OK, and it's provided this 6-graph summary for me for a report that I didn't have to build. I didn't have to create it. Someone else already did it, leveraging that power of community. One of the things I like about this is you can color the out-of-spec points and see it across all of the different graphs. And then if I wanted to share that, it's very easy to do. I can create an interactive HTML and then just open it and send it to somebody who doesn't have JMP, who can then play around. So let's just view that. There we go. And I can send that, and you can see it's got my colored points as well, and they can see my analysis that I've done and click around for themselves. So another great category of extensions that we have on the JMP marketplace are actually Pythonic add-ins. So leveraging the power of open source Python libraries to do data analysis for me within JMP. So one that was created by another great JMP staff member, Russ Wolfinger, is the Profit Time Series Forecasting extension. It uses the Facebook Research Profit Library based on various different types of time series forecasting, either historical data, holiday data, seasonal data. And we're going to examine this river data that we have here. So we're just going to click download, once again, our favorite step on the app, agreeing to the user agreement, and then click open, installs. Let me just close these out. Okay. And then within our add-in menu, you can see that we now have the Profit Time Series Forecasting extension installed. And this one has a couple different steps. So if you wanted example data, it's got that river data. It has a help menu. And then you can also check to make sure you have all of the appropriate Python packages installed already. So again, we're going to pull our data from the cloud, and we're going to just use this add-in, click Profit Time Series Forecasting. We'll set our variables, so we have our time and our mean river data and daily forecasting. And so we have a bunch of different options. These are all provided by the Python library that Russ has created as a no-code interface within JMP. So it's a daily, and let's view it for 3 months out. Click OK. And we can see it did pretty well based on the historical data. It did that 3 months based on previous years and seems to be pretty in line with what we would expect. Additionally, we have all of the data here that we can analyze and do more analysis on. We can see the weekly trends, the daily trends, the yearly trends, and how it got that forecast. So we can really dive into the information and do more with it. And so that's really just how the JMP Marketplace in 2 steps can get your data analysis going. There's so many great extensions to be found on the JMP Marketplace from a beginner level, learning JMP. We have a Learn bot, which is a chat bot to help you just with those daily JMP processes that you might be doing, the student add-in, the data analysis director to get you started. In addition, we have more advanced extensions, so like your XGBoost, your Torch Deep Learning, those more advanced machine algorithm extensions as well. And with that, I will hand it back to Jules.
Thanks, Kristen. So this morning we've seen that the magic of JMP comes down to things that JMP enables, things that encourages, things that it eliminates, and also things that it helps you avoid entirely. But I do think there's one more thing that makes JMP magic across the entire workflow, and it's how JMP makes you see yourself. And I think this is really important because how we see ourselves using this piece of software is absolutely going to impact the choices we make when we're using it. Now, there's actually a fun effect in psychology and virtual reality I want to tell you about. There's a reason. It's called the Proteus effect. Proteus in Greek mythology was a god of the sea. He was known as a shapeshifter. He could also predict the future, I think, by looking into the ocean. He had some other cool powers. But for our purposes, it was that he was able to change shape. And the Proteus effect within the psychology literature describes the fact that when people are in virtual reality spaces, their avatars, the ones that are given to them in experimental cases, impact their behavior. And this has been shown in meta-analyses. It's a robust effect. To give you a simple example, if we randomly assign people in a virtual space to have different heights, so a taller avatar versus a shorter one, the people randomly assigned to have a taller avatar are more outgoing in the virtual space. Pretty cool effect. I think it's rather unsurprising. The way that we see ourselves in an environment certainly makes sense that it would impact our behavior, but it is pretty cool that it shows up in virtual reality. I think this actually happens with any software, any interface where we see ourselves. And of course, in this case, I'm talking about JMP. I think how we see ourselves in JMP actually impacts the way that we make choices with our data. And so I want to give you a quick example of this inside of JMP in a way that I think, because, and I've been using JMP for a while, I feel like I'm pretty ambitious in the software. It leads me to make choices to do certain things that I normally maybe wouldn't do in other pieces of software. And so the context of this is, I was talking with a friend about a few months ago maybe, about this conference, and I was saying it's in Berlin, and she asked, what's the weather gonna be like in Berlin? The easy answer would have been to go to Google and actually give her the forecast for Berlin in March. Instead, I wanted to do the much more complicated thing, and I wanted to give her a point of reference. She lives in Toronto, by the way. And so I wanted to say, what month in Toronto is most like Berlin in March? Which is a much harder thing to Google. But it is a pretty easy thing if you go and grab a bunch of data. While it's opening, I'll show you where this comes from. It's actually a data set on Kaggle that somebody's keeping updated with weather for 100 cities across the world, and it has hourly data for the last 5 years. Really cool data set. So here I am in JMP. This is about 4.25 million rows. And we have to do a number of things to get to that answer. What month in Toronto is most like this month in Berlin? And so I'm going to do some of these things quickly. The point is not to actually show off the process so much as show that we can be so ambitious. I'm going to do this on the basis of temperature. So we're going to get rid of some columns just to keep ourselves sane. I actually know that this date time is not local time for those areas. It's actually UTC. It's time in Germany. Not Germany. In, what's our base time at 0? Greenwich Mean Time. So we actually have to update that. So there's this metadata set that they include. It has the UTC offset. It's stored as characters. So I'm going to do some things to clean this up. I'm just going to text to columns, put a colon. We're going to break apart that 4, because that's what we need. I'll make it continuous. I'll take away those columns. We're going to use a really neat thing in JMP, which is a virtual join. I'm going to make that city name a link ID. I'm going to go in and link reference that from this table. And what that does is brings in that column, the UTC offset. And so now that's in the data set. I can use that. So we need to update the date time. We could make a formula column separately, but I'm going to do something here. I'm going to use the new formula column formula, which gives a special version of the formula editor so we can do an in-place data update. I'm going to take our date time. I'm going to add on to it that reference data of the offset, and I'm going to tell JMP that that's actually in hours. So if you look here, 12 a.m. is about to become 4 a.m. Cool, that's done. So we can drop the link reference. We don't need it, and we don't need this table. So one step down. Okay, the next thing we have to do is build ourselves a month out of this date time. We can do that as a new formula column. I'll do date time, and I'll do the month abbreviated, which is going to give us text. And the reason I want to do this is I want to take that month abbreviated column, and I'm going to concatenate it against the city date, or city, which gives us a city month column. And I'll actually just call it city month. City month. And the reason we're doing this is that's going to be the sort of comparison column or data we're going to use. I could take month, and we don't actually need that anymore, so I'll hide it. The date time, we're going to also create a time variable out of. So I'll go here and do time of day. So we have our time of day as well. And so we're nearly there. We have to restructure the data a little bit to get a closeness measure that we want to make. So I'm going to use table summary. And I'll turn on the preview, because here's what we're going to do. We're going to have rows as the city month. We're going to have columns as the time of day. And we're going to have the metric be the temperature in the city. I'll do the mean. And I'll actually take away the n there. We'll just call this summary. And I want the statistic at the top to just be the column. So it says temperature at a time of day. Okay, so we have a column or a data table now that's wide. This is the profile of the time of day effect for every city month averaged over those 4 years and all the days within the month. And so what we're going to do here is we're going to use a statistic to get a closeness measure. I love hierarchical clustering for this. And so we're going to label by the city month. We're going to use all those columns. We're going to tell data that we don't want to standardize. These are all columns on the same range, and so we want to use an unstandardized form. We get a dendrogram, and if you've never seen these, I'll just zoom in. This is like a closeness measure of city months now. So if I grab a clump of these, we can kind of see what's happening. I'll pop into a data view. I'll take those temperatures, put them on the X. Let's put a line on, and we'll city month as an overlay. It's picked out the profiles that are the most close across those city months. And so that's just one tiny subset of the whole data. If we zoom back out, you can see this has happened for the whole data table. And so what I want from this is I'm going to extract a distance matrix. So this is going to be a square matrix of every city month against every city month. I want it in a slightly different format. I want it to be stacked. And so I'll actually take all of those columns because we're going to have a distance column for the city months. And what this will give us is a format that it's a little easier to find the related city months, I should say here. And so I'll get rid of that square matrix. You'll notice that there are zeros in this. So if I sort ascending, it's because we have city months that are next to themselves. And so I'm just going to get rid of those city months here. And now we have distance. So the closest in this entire data table, Leeds in September to Manchester in September. Okay, that makes sense. To give us a visual, let me actually do something here. I'm going to grab those temperatures. I'm going to use an add-in. I did just for this talk because I thought it'd be cool. And we'll call this like daily profile. And this is going to build me a little graphic for the profile of temperature. And let's use that same link ID trick we did before. And I'll go back into this table, link reference. This is going to give us, if I unhide that column, which I'll stick at the start, it's going to give us that little daily graph. That's for Leeds, because that was the first one I link referenced. I'll do the same thing for the city month. And it's going to give us for the second, I'll unhide that. That's going to give us the second profile. And so now we can actually compare. I'll hide the side there. We can actually see, oh, of course, Leeds in September does look like Manchester in September. The least similar is Montreal in January versus Kuwait City in July. Okay, we've proven that this makes sense. So let's actually get the answer for my friend. I'm going to use something in Jump 19. We can just filter this table directly. And so I'll click on the header. We have a filter. And I'll say, only show me Berlin in March. And so there is my Berlin in March data. And so Busan in February is the closest. Again, the least likely is Kuwait in July. But we're going to do an and here, and I'll say, OK, for the city month, for the reference city, let's see Toronto. And let's see, for all the months in Toronto, turns out it's November. So I can answer the simple question my friend asked me in a really complicated way and say, imagine November in Toronto. For her, Toronto in July is the least. In fact, where in July is the most like Berlin in March? Melbourne in July. That makes sense. Southern Hemisphere, or Buenos Aires. So the point of this is not that this is a good analysis, because frankly, it's probably not, and there's statistical questionable things about it. The point is that because I'm a JUMP user and have used the software for a while, I feel ambitious in the software. It makes me feel powerful with this type of data. And I think that's really important, because how JUMP makes you see yourself is going to impact the work you do. And I hope that JUMP helps you see yourself as powerful and capable, because if we go back to that initial plot, right, this person does not see themselves as powerful and capable. But they don't have to. I mean, even with AI, we can start to coax it towards feeling empowered. Here they are a little bit more empowered. Suddenly they have more screens. That's good. We can say even more empowered. What are they going to be like? More screens, right? We can keep on the right track, keep going. I don't know what AI thinks that's what power is here. But if I keep pressing it, they get potentially a little bit more abstract. And suddenly now you're the entity at the center of your data universe. And I just, for fun, show me the ultimate power with data. And so this is a JUMP user, right? So I'm kidding around here. But of course, how we see ourselves, right? How JUMP helps you see yourself is really important. So I do want to leave with one question, which is, how does JUMP help you see yourself? because I see it as our job in development, and my job specifically, to make sure that JUMP helps you see yourself as capable, as powerful, because no matter what your background is, no matter what your skill sets are, I really think with JUMP you can be. So throughout the conference, if we're not helping you achieve that, come and talk to us. Tell us what will make you feel powerful in JUMP. So with that, I'll turn it back to Jeff. Thanks so much for your time.